Hello, my name is Madison Jaslovicius, and I'm going to be talking to you about carbonic acid today. I'm going to walk you through a few little things you can do, like electron configuration, loose dot structure, all kinds of fun stuff. So let's get to it. So carbonic acid is a molecule. Its formula is H2CO3. We're going to find the electron configuration of HC and O. Electron configuration is going to be the distribution of electrons in the different orbitals. We utilize the off-ball principle because with the off-ball principle, we know that you start at the lowest energy level and work your way up. So this infographic here, N represents the energy levels, L represents the shape. That's the principal quantum number and the angular quantum number. So with 1s2, you look at energy level, shape, and number of electrons. You can find the number of electrons by looking at the periodic table. That is the atomic number. So for hydrogen, you have 1, so we're going to do 1s1. For carbon, you have 6. Doop, doop, doop. For oxygen, you have 8. So 1, 6, and 8. Finding the electron configuration is really great because you can also find the valence shell. The valence shell is going to be home to the valence electrons. The valence electrons have the highest energy, and those are going to be pretty crucial when you're doing loose dot structures. Because they have high energy, they are what are responsible for the bondings. So these guys are going to be our valence electron shells because they're in the last place. One way to find valence electrons is to look at the top of the periodic table. These numbers right here tell you the number of valence electrons. So for hydrogen, you have 1. Carbon, you have 4. And oxygen, you have 6. So as a little precursor to loose dot structures, we can also talk about valency. Valency is the number of bonds that each of these guys can make. One way to kind of visualize it better is to actually draw out the valence electrons for each of these. So I said 1 for hydrogen, 4 for carbon, and 6 for oxygen. So again, valency is the number of bonds. So I know hydrogen can only make 1 bond, because 1x right here. So that's valency of 1. Carbon has 4 empty spots, so it can make 4. And oxygen has 2, so it can make 2 bonds. So that's our valency of each of these guys. If you're going into loose dot structures, this is incredibly important because then you can actually make the correct structures. Now, loose dot structures have 5 simple steps. The first step would be to find the number of valence electrons for the entire molecule. So looking at our formula, we have H2CO3. So we know that hydrogen has 1, carbon has 4. There's a number of valence electrons. I'm just going to multiply them by the quantity. We have 2, 1, 3. Adding these all up together, we have 24 valence electrons. Woohoo! Now we're going in with the total number and the valency. We can do step 2, which is draw out the general layout of these 3 guys. So I'm going to start off with carbon because it's our central. C, O, 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 and hydrogen. I think that's a pretty logical, good first layout. So our next step is going to be to make bonds with all of these guys. So bond is 2 valence electrons. So I'll start off with hydrogen, because it's simplest, 1. Kind of work my way in, making bonds with everyone. So already that is 10 valence electrons gone out of 24. So everyone's bonded up. Our next step is to disperse the remaining 14 valence electrons. We're going to try to follow the octet rule, which means that each of these guys would love to be as close to noble gas configuration as possible. These guys have 8 valence electrons. These guys want 8 valence electrons. So these guys can share well, so we're going to try to make everyone happy. Start off with the oxygen, give him a full one. This guy too. Now when you get to carbon, you realize that this guy already has 6 through pairs. And this guy needs to 4 more. Sorry, 6 more. So what I'm going to do is I'm going to make this a double bond. Boop. That makes carbon happy and also helps him get closer. Then I'm just going to fill him out. And ta-da, if you count it up, we have 24 valence electrons. Everyone's shared equally. Everyone's pretty happy. Everyone's at octet. We're in a good spot. So our next step, once we're done with this, is going to be to find the formal charge of all 3 of these elements. The formal charge can be found by subtracting the valence electron number from the number of bonds plus the number of free electrons. So that means these guys, these 3 electrons. So for hydrogen, we're going to have 1 valence electron minus 1 bond plus 0, that equals 0. For oxygen, we have 2 bonds, 6 valence electrons minus 2 bonds plus 4 free electrons, that equals 0. For carbon, you start off with 4 valence electrons minus 4 bonds plus 0 electrons equals 0. Now, one thing I kind of glossed over for the sake of brevity is that not every molecule starts off as neutral when you're making loose dot structures. We're very lucky and ours did start off as neutral. So when you're finding the formal charge, you're going to try to get the same charge as this guy. If not, you did something wrong. But we're happy campers. We did it right. So, I also think this is a good time to talk about Renaissance structures. Renaissance structures are basically the average of the different structures that you can make. What it really means is that this formation compared to this formation are going to be the same quantity-wise. So, like, these still have the same number of electrons, same number of pairs, they're just in different spots. They really mean the same thing, it's just the average total of all the different ways that you can make these structures. So, here's 2 possible Renaissance structures for our molecule. Woohoo! So now, moving on, I would like to talk about electronegativity. Actually, let's keep this out. So, electronegativity is going to be the amount, it's going to be how much one element likes another. So, on the periodic table, the general trend is the lower you go, the less electronegative you get. The more to the right, the more electronegative you get. So just by kind of glancing at the periodic table, you can see that hydrogen compared to carbon and oxygen is going to be the least. And oxygen, because it's more far right, is going to be the most. And fun fact, these are also, hydrogen, because it's the least out of those 3, is also the lightest according to the atomic mass. So it's going to be the smallest atom, and oxygen is going to be the largest atom according to the atomic mass. So that's a fun parallel to look at. So, talking about electronegativity, each of these guys also has a number. I wrote them down for you. Hydrogen has a 2.1, carbon's 2.5, and oxygen's 3.5. Now, we use these numbers to kind of predict how how electrons bond together, and we can quantify those bonds as polar, ionic, and nonpolar. Typically, anything with a number greater than 1 is going to be ionic. The only exception is going to be hydrogen, because anything that bonds with it is just incredibly polar. It's just so massively polar. And so, looking at our loose dot structure, you can see that we have 2 different kinds of bonds. We have carbon and oxygen and hydrogen. Now I went ahead and subtracted out those numbers so you can see the difference. Oxygen is 3.5 minus 2.5, so it's 1. And oxygen and hydrogen is a 3.5 minus 2.1, so it's 1.4. So I'm going to go and say both these guys are polar. Hydrogen because it's a hydrogen bond, and oxygen carbon because it's a 1. So when you're talking about polar bonds, you can also assign which end of the bond is more negative or positive. For that, we use delta notation. That's these little guys, little G's with a plus or a minus. And this bond right here, oxygen, because it's a 3.5, is much more electronegative than hydrogen. So he gets the negative and hydrogen gets the plus. Then down here with the carbon is more electronegative than the oxygen. Or sorry, I said that wrong. The oxygen is more electronegative than the carbon. So he gets the minus as well. So that's just a little look at our polar bonds we have going on here. Sorry. Another thing I would like to talk about is here, pull this guy back out, is the shape of our molecule. We're very lucky, and our molecule is actually all on the same plane. So I don't know if you've seen any electron geometries before where they're coming towards you or coming at you or behind, but ours is all on the same plane. And ours is actually going to be called the triangular planar. So we have no free electrons, woohoo! But we do have 3 areas of dense electron bonding. So the areas would be 1, 2, and 3. But they're all on the same plane. Very bad artist, but it looks very similar to this guy right here. But that would be our electron geometry. Trying to make sure I covered everything. I've been practicing this a few times and I finally got through it pretty quickly. But again, thank you so much for listening. I really appreciate it. I hope that I covered everything for you. And yeah, that is carbonic acid. I would tell you chemistry jokes, but all the good ones are gone. Ooh, that was bad. Again, thank you for listening. I hope you have a great night. Bye.